Space is not just beautiful, it is profoundly weird. Scientists are constantly finding cosmic oddities, strange new phenomena that defy our best explanations. These are not just distant lights, but genuine mysteries, from a star that dims in impossible ways to a galaxy with no stars at all. By the end of this journey, you will have explored 30 of the most bizarre and recent discoveries that are reshaping our understanding of reality. We will see a black hole racing through the void and a planet where it rains gemstones. What cosmic surprise do you think could change everything we know? Our first oddity is a shadow on a giant, a persistent chill in the swirling chaos of Jupiter's atmosphere. While the famous Great Red Spot is a centuries-old storm of immense heat and fury, scientists using Earth-based telescopes discovered another, more subtle mark. They call it the Great Cold Spot, a vast dark region in the planet's upper atmosphere, thousands of miles across and hundreds of degrees colder than everything around it. This is not a storm cloud, but a hole in the atmospheric heat, a profound and enduring cold sink etched into the polar sky of the solar system's largest planet. Its very existence is a thermal paradox. Jupiter is a world of immense internal heat, left over from its violent formation, and its upper atmosphere should be a relatively uniform blanket warmed by the auroras dancing at its poles. Yet here, this spot persists, a frigid island defying the planetary warmth. The leading theory points to those very auroras as the culprit, but in a surprising way. The tremendous energy from Jupiter's powerful magnetic field, which creates the brilliant light shows, might also be driving a kind of atmospheric shadow. This energy could be funneling heat away from a specific region, or triggering complex waves in the atmosphere that redistribute energy and leave behind this persistent cold patch. What truly baffles researchers is its longevity. Unlike transient weather patterns, the Great Cold Spot appears to be a permanent, or at least a semi-permanent fixture. Data suggests it has been there for over 15 years, possibly much longer, constantly reforming and maintaining its identity against the planet's turbulent flows. This durability is the core of the mystery. How does a structure so cold survive, unchanging, in an atmosphere famed for its chaos? Visuals from missions like Juno, showing swirling cloud tops and maps of atmospheric temperature, reveal this dark blemish not as a cloud but as a profound thermal fingerprint. It is a ghostly imprint of a hidden process, a reminder that even on a world we have studied for centuries, the atmosphere holds secrets written not in color but in degrees of cold. That persistent cold spot on Jupiter is a mystery of absence, a missing heat. But what about a star that seems to have something in front of it, something vast and strange, blocking its light in ways nothing natural should? This brings us to our second oddity, a star that refuses to be explained, a cosmic beacon of unanswered questions known as KIC 8462852, or more famously, Boyajian star. Years after its initial discovery, this star remains one of the most perplexing objects in our galaxy. Its signature behavior is a series of dramatic, irregular dips in brightness. We are not talking about the gentle, rhythmic dimming of a planet passing by. These dips are deep, up to 22% of the star's light vanishing, and they are chaotic. They last for days or weeks with no predictable pattern, as if giant, jagged shapes are drifting in front of the star in a slow, silent dance. The latest data from continued monitoring has only deepened the puzzle. The dips are not stopping. New, unexpected dimming events continue to be recorded, each one a fresh data point that seems to break the rules. The initial, breathtaking idea that captured the public's imagination was, of course, the possibility of alien engineering. Could these be the shadows of a Dyson swarm, a vast collection of energy-collecting structures built by an advanced civilization encircling their sun? It is a compelling science fiction image, and the star's behavior does not outright dismiss it, which is perhaps the most thrilling part. Yet astronomers have diligently searched for more conventional answers. The first major theory proposed a giant swarm of comets, hundreds of thousands of them, shattered and creating a huge cloud of dust and debris. But to cause the observed dips, this comet family would have to be impossibly large, and the star shows no excess infrared heat, which such a massive dust cloud should produce. Other ideas include the aftermath of a planetary collision, or intrinsic variability of the star itself, but none cleanly match all the bizarre observations. The truth is, no single explanation fits perfectly. Each theory solves one part of the mystery while creating another. This star is a cosmic riddle written in light, its irregular heartbeat a signal we are still learning to decode. Visuals of its jagged, plunging light curve tell a story of profound obstruction, while artistic depictions of a hypothetical Dyson swarm capture the scale of what such an answer would mean. Boyajian's star stands as a humbling reminder that sometimes the universe presents us with a phenomenon so odd that our catalogue of natural explanations simply comes up short, leaving the door to wonder, however slightly, still open. The debate over Boyajian's star centers on what might be blocking its light, a question of something unseen in its path, but sometimes the oddity is the object itself, a visitor from another star system that refuses to follow the simple rules. In 2017, our solar system received its first known interstellar guest, a small, fast-moving object later named Oumuamua. Its arrival was a monumental discovery, but its behavior quickly became the real mystery. As it sped away from the Sun, telescopes tracked something unexpected. Oumuamua was accelerating ever so slightly on its exit trajectory. This was not the pure, predictable arc of an object governed solely by the Sun's gravity. Something else was giving it a gentle, continuous push. For comets, this is common behavior. The heat of the Sun vaporizes ice on their surface in a process called outgassing, and the jet of released gas acts like a natural rocket engine, nudging the comet along. The immediate assumption was that Oumuamua must be a comet too. Yet, when scientists looked for the telltale signs, they found nothing. No surrounding cloud of dust, no visible coma of gas, no tail streaming behind it. It was accelerating in silence with no observable outgassing at all. This launched a fierce and ongoing scientific debate. If it was not a typical comet, what was providing the thrust? One compelling theory suggests Oumuamua was a chunk of solid nitrogen ice, a kind of cosmic iceberg. As the Sun warmed it, the nitrogen would sublimate directly from solid to gas, potentially providing a faint, invisible jet that could explain the acceleration without creating a dusty tail. Another, more exotic idea proposes it was a hydrogen iceberg. In the cold depths of interstellar space, molecular hydrogen could freeze solid. But near the Sun, that hydrogen ice would sublimate rapidly, again providing thrust while leaving almost no visible trace. The challenge is that both materials are fragile and would struggle to survive a long journey between stars. Visuals of its tumbling, elongated path show an object tumbling chaotically, not spinning smoothly like a crafted ship, its motion adding to the enigma. Artist concepts depict it as everything from a pancake-shaped slab to a cigar-shaped rod, attempts to match its strange brightness variations. The core of the debate is not just about one object's composition, but about the very nature of material between stars. Is the galaxy filled with fragile icebergs of exotic ices, unseen until one tumbles through our neighborhood? Oumuamua's silent acceleration remains a fingerprint of an unseen force, a tiny push that challenges our categories and reminds us that the first visitor from the great dark will not be easily explained. Oumuamua's silent acceleration was a puzzle of absence, but the universe soon provided a contrasting clue. Just 2 years later, in 2019, a second interstellar object was spotted entering our solar system, and this one played by the rules. Named 2I/Borisov after the amateur astronomer who first saw it, this visitor was immediately recognizable as a comet. It had a brilliant, fuzzy coma and a distinct tail streaming behind it, a classic display of outgassing as the sun warmed its icy core. Here was an interstellar guest that behaved exactly as expected, a wandering snowball from another star. The discovery of Borisov was profoundly reassuring in one sense. It proved that Oumuamua was not the only model for interstellar objects. The galaxy is apparently filled with both the strange, like Oumuamua, and the familiar, like this comet. But in another way, Borisov deepened the mystery of its predecessor. If comets like Borisov are common, what does that make Oumuamua? Its bizarre, tailless acceleration now seems even more exceptional. Scientists eagerly studied Borisov's composition as it passed, finding its chemical signature was unlike any comet from our own Oort cloud. It contained unusually high amounts of carbon monoxide, a gas that freezes at very low temperatures, suggesting it formed in a different, colder part of its home star system, or around a different type of star altogether. This was a direct, tangible sample of material from another planetary family, delivered to our doorstep. The existence of two such different visitors in just 2 years suggests a staggering implication. These interstellar interlopers are not rare. Current estimates based on these detections suggest there could be thousands of them within the orbit of Neptune at any given time, all passing through unnoticed. We simply have not been looking hard enough or with the right tools. This is where our next great leap in discovery begins. The upcoming Vera C. Rubin Observatory, a massive telescope being built in Chile, is designed to conduct a relentless 10-year survey of the entire southern sky. Night after night, it will scan the heavens, and its powerful camera is expected to detect dozens, perhaps even hundreds, of these interstellar visitors. Each one will be a new data point, a new piece of the puzzle. Are most of them conventional comets like Borisov, or will we find that a significant fraction are odd, dark, and perplexing like Oumuamua? The answer will rewrite the story of our own solar system's birth. These objects are cosmic debris, the leftover building blocks ejected from infant star systems. By catching and studying them, we are collecting samples from distant stellar nurseries without ever leaving home. They tell us what ingredients are common across the galaxy and what strange recipes other stars use to cook up their planets. The search for these faint, fast-moving dots of light is about to explode, promising a new era where the odd becomes the ordinary, and every night could bring a visitor from a sun we will never see. If interstellar visitors are the lone wanderers of the cosmos, some galaxies are ghost towns on a far grander scale. Our fourth oddity is a place where the lights have simply never turned on. It is a galaxy called a GC114905, and it is one of the most baffling structures ever observed. Imagine a galaxy the size of our own Milky Way, with all its vast volume and gravitational might. Now imagine looking at it through the most powerful telescopes and seeing almost nothing. No brilliant spiral arms, no glowing core of billions of stars, just a faint, diffuse smudge against the dark. That is this object. It is an ultra-diffuse galaxy, but it takes that category to an extreme. Observations show it contains virtually no stars, perhaps a handful where there should be hundreds of billions. What you are seeing in that faint smudge is not starlight, but the dim glow of hydrogen gas spread so thin it is almost transparent. So what holds this immense, empty structure together? The only answer that fits is an enormous amount of dark matter. This galaxy appears to be a near-pure dark matter halo, a ghostly skeleton of invisible mass that somehow gathered an ocean of gas but completely failed to spark the fire of star formation. This existence strikes at the heart of how we think galaxies are born. The standard model is elegant. First, a vast cloud of dark matter collapses under its own gravity, forming a spherical halo. Then, ordinary gas, drawn in by that dark matter's pull, cools, condenses, and fragments into stars. The stars light up and a galaxy is born, but a GC 114905 followed only the first step. It built the dark matter scaffold and collected the gas, but the star-making machinery never kicked in. Why not? Visuals here are crucial. A side-by-side comparison with a spiral galaxy like the Milky Way shows a shocking contrast. One is a dazzling pinwheel of light, the other an empty, ethereal bubble. Simulations of dark matter halos show them as intricate, web-like structures, the cosmic framework upon which everything visible is built. This galaxy is that framework, naked and exposed. The mystery forces two profound questions. First, is our understanding of dark matter wrong? Perhaps in certain environments, dark matter interacts in ways that prevent gas from cooling and collapsing. Second, and just as puzzling, is our understanding of the gas itself flawed. Could something have kept it stirred up and too hot to form stars, like a cosmic whirlpool that never settles? This dark galaxy is a cosmic paradox, a place where all the ingredients for a glittering metropolis are present, yet it remains a silent, empty vault. It challenges the very recipe for building a universe, suggesting that for every rule of cosmic construction, there exists a quiet, shadowy exception. While dark galaxies represent a failure to ignite, the universe also creates engines of incredible violence that can be thrown from their homes. Astronomers using the Hubble Space Telescope have spotted something that should be impossible: a supermassive black hole, an object weighing as much as 20 million suns, hurtling through intergalactic space at tremendous speed. It is not drifting quietly, it is racing away from a distant galaxy, and in its wake it is not leaving destruction but creation, a narrow corridor of brilliant newborn stars. This is not the behavior of a cosmic predator, but of a runaway engine, a titan on the lam. The image is startling: a single, compact quasar, the blazing signature of a feeding supermassive black hole, is seen far from the bright core of its host galaxy. Behind it stretches a thin, almost straight line of intense blue light, a stellar contrail 55,000 light-years long, twice the diameter of our Milky Way. That blue light is the signature of hot, young stars, a stellar nursery forged in the black hole's chaotic exit. How does a black hole, the most gravitationally dominant object imaginable, get kicked out of its own galaxy? The answer lies in a cosmic dance of unimaginable power, a gravitational slingshot. The leading theory begins with a galactic merger. When two galaxies collide, their central supermassive black holes eventually sink to the new combined core, forming a binary pair that orbit each other. But if a third galaxy, and thus a third black hole, joins the fray, the dance becomes unstable. In a complex gravitational interaction, one of the three black holes can be flung outward at incredible speed, like a stone from a sling. This is precisely what scientists believe happened. The runaway black hole was likely the odd one out in a three-body interaction, ejected from the galactic core. But the story of its star-forming trail is even more fascinating. As the black hole plows through the tenuous gas that surrounds the galaxy, it is not consuming it quietly. Instead, the immense speed of its passage, likely over 4 million miles per hour, compresses and shocks the gas in front of it. Think of a boat plowing through water, creating a wake of churned foam. In this case, the black hole's bow shock squeezes the thin galactic gas, cooling it and triggering it to collapse under its own gravity. The result is a chain reaction of star birth, a literal trail of stars left in the hole's path. Visualizing this requires a dynamic sequence, the chaotic merger of three galaxies, their black holes whirling in a deadly ballet, and then the sudden, violent ejection of one. We see it streaking away, its gravitational influence not pulling material into an accretion disk, but ramming into the surrounding medium, compressing it into glowing knots of blue light that ignite into new suns. This discovery shatters the simple image of black holes as stationary monsters at the centers of galaxies. It reveals them as dynamic objects that can be sent careening through the void, and in their violence they can become unlikely midwives, seeding the cosmos with new light as they flee their past. A black hole racing through space is a titan on the move, but even the monsters that stay at home can have a pulse. Deep within our own galaxy, about 35,000 light-years away, a unique stellar mass black hole is sending out a signal so rhythmic it has been called a cosmic heartbeat. The object is a microquasar known as GRS 1915+105, a black hole locked in a tight orbit with a normal star. As it pulls material from its companion, that gas spirals inward, forming a superheated, whirling disk of plasma before vanishing past the event horizon. But this accretion disk is not a steady, silent whirlpool. It pulses. About every 50 seconds, the system erupts in a powerful, predictable burst of X-rays, a flash so regular you could almost set a watch by it. This is not a simple flicker. It is a fundamental oscillation of the entire inner accretion disk, a rhythmic expansion and contraction driven by the intense physics at the edge of oblivion. Scientists call these quasi-periodic oscillations, and while many black hole systems have them, none are as stable and persistent as this one. The heartbeat continues for a while, then stops, then starts again years later, as if the black hole is taking a breath. What creates such a precise rhythm in a place of such chaos? The leading theory is a delicate and violent balancing act. As material floods into the inner disk, it heats up tremendously from friction and gravitational compression. This heat increases the radiation pressure, the outward push of light itself, until it becomes strong enough to overcome gravity's inward pull for a moment. The inner edge of the disk puffs outward like a balloon inflating. That expansion allows the trapped radiation to escape in a massive burst, the X-ray pulse we see. With that energy released, the pressure drops, gravity wins again, and the disk contracts back, pulling in fresh material to start the cycle over. This 50-second heartbeat is a direct window into the extreme environment just outside the event horizon. By studying its rhythm, astronomers can measure properties of the black hole itself, like its spin, and test the laws of physics in a gravitational field so strong it warps space and time. Visuals here are key. The X-ray light curve data looks like a clean, repeating spike on a graph, a stark contrast to the violent, random fluctuations seen from other black holes. An artist's impression shows the swirling, multicolored accretion disk with its inner region rhythmically glowing brighter and dimmer, a lighthouse flash in the high-energy universe. This heartbeat tells us that even in the most destructive places, nature can impose an order, a predictable cycle of buildup and release that turns a cosmic vampire into a metronome, ticking away the seconds as it feeds. That rhythmic heartbeat is a clockwork of destruction, but some cosmic collisions unfold over eons, their violence written across the sky in sweeping brushstrokes of light. The Hubble Space Telescope recently captured a breathtaking portrait of such an event, a pair of galaxies caught in a slow-motion feast. This is NGC 7727, and it has earned a dramatic nickname, the Cannibal Galaxy. The image is one of beautiful chaos. You are not looking at two distinct spirals, but at a single, tangled mass. The cores of the original galaxies, now two bright, off-center knots of golden light, are still visible like the eyes of a cosmic beast. Swirling around them are vast, distorted streams of stars and dust, immense tidal tails that have been pulled out by gravitational forces over hundreds of millions of years. These are not solid arms, but rivers of suns, entire stellar neighborhoods flung into deep space by the galactic dance. This is the late stage of a merger, a process that is both destructive and profoundly creative. As the two galaxies intertwine, their immense gravitational fields do not just tear each other apart, they stir the cosmic pot with unimaginable force. Giant clouds of gas and dust, which might have drifted quietly for eons, are suddenly slammed together. This violent compression triggers a firestorm of star birth. Throughout the chaotic structure of NGC 7727, brilliant blue clusters ignite, pinpointing regions where new suns are flaring to life in stellar nurseries created by the collision. The eventual fate of this system is written in the physics of such mergers. All that swirling, chaotic motion, the energy of billions of stars orbiting in a new, combined gravity well, will gradually settle. The distinct spiral structures will be completely erased, smoothed out into a vast, featureless blob of stars. What will remain is an elliptical galaxy, a smooth, egg-shaped collection of older, redder stars with little gas left to form new ones. The merger is the galaxy's final burst of youthful creativity before a long, quiet retirement. To truly appreciate the scale and inevitability of this process, a side-by-side view is stunning. On one side, Hubble's crisp, detailed photograph shows the real cosmic wreckage, the delicate filaments of dust and the piercing blue star clusters. On the other, a supercomputer simulation shows the same event from beginning to end, two spiral disks approaching, their stars represented as millions of glowing points. They pass through each other, their shapes stretching into those iconic tidal tails, then swing back for another pass over and over, until they finally coalesce into a single, smooth ellipsoid. Seeing them together bridges the gap between a single snapshot and a billion-year story. This cannibal galaxy is not a monster, it is a natural phase of cosmic evolution, a reminder that the majestic spiral we call home, the Milky Way, is on a collision course with the Andromeda Galaxy. In several billion years, our night sky will undergo a transformation just as violent and beautiful, a final merger that will reshape our celestial neighborhood forever. Our own galactic neighborhood hides a phantom structure of staggering scale, while the cannibal galaxy shows a violent past written in starlight. Much closer to home, astronomers have mapped a different kind of cosmic aftermath, one we cannot see with our eyes at all. This is our eighth oddity, a colossal, faint bubble of radio waves known as Loop 1, a ghostly sphere that envelops a significant part of our local sky. Imagine a cavity in space over 300 light-years across, its walls glowing with the faint echo of a cataclysm that occurred millions of years ago. That is what Loop 1 appears to be, the ancient remnant of a supernova, a star that died in a titanic explosion so long ago that its visible light faded eons before human history began. What remains is the expanding shockwave of that blast, a shell of energized particles and magnetic fields that still ripples through the interstellar medium, emitting a whisper in radio frequencies. For decades, it was just one of several large, mysterious radio arcs in the sky, its true nature and distance poorly understood. But recent surveys, particularly from the Planck satellite and ground-based radio telescopes, have pieced together a three-dimensional map of our local interstellar space, and the result is breathtaking. We do not live in a uniform sea of stars and gas. We reside inside a complex of overlapping bubbles like Swiss cheese, each one carved out by ancient stellar explosions. Our solar system sits within a cavity called the local bubble, which was itself blown clear by a series of supernova roughly 10 to 20 million years ago. And now the data reveals that Loop 1 is another, slightly older bubble, and its expanding shell is actually colliding with our local bubble. Visualizing this requires a shift to a three-dimensional model. Picture our position not as a dot on a flat map, but as a point within a cosmic foam. The local bubble is an irregular cavity about 1,000 light-years wide, with our sun drifting near its edge. And pressing against one side of this cavity is the vast spherical structure of Loop 1. Where their surfaces meet, the interstellar gas and magnetic fields are compressed and tangled, creating a complex, turbulent boundary layer that influences the environment for light years in every direction. This ghostly bubble is not just a fossil, it is an active participant in shaping the space around us. Its magnetic fields can deflect some cosmic rays, and its structure influences how other clouds of gas move and eventually collapse to form new stars. The discovery that we can map these ancient explosions in 3 dimensions and see how they intersect changes our understanding of our own cosmic address. We are not just passing through a random part of the galaxy, we are navigating the intricate, layered aftermath of stellar lives and deaths, a history written in invisible radio light across the sky. These ghostly bubbles are the slow echoes of ancient stellar death, but some of the universe's dead stars refuse to fade quietly. They announce themselves with a rhythmic beat, a cosmic lighthouse ticking with such precision it defines an entire class of object. We call them pulsars, the rapidly spinning cores of massive stars that exploded as supernova. Typically, they flash at us anywhere from milliseconds to a few seconds, their beams of radiation sweeping past Earth like a searchlight from a spinning neutron star. This rhythm is so reliable that finding one with a different pulse is like finding a clock that ticks once a day. Yet that is exactly what astronomers have found. A mysterious object, catalogued as GPMJ 1839-10, emits a brilliant pulse of radio waves not every second but once every 22 minutes. This is not a slight variation, it is a fundamental challenge. For over 30 minutes during each pulse, it becomes one of the brightest radio sources in the entire sky, then vanishes into silence for the next long interval. This behavior is so far outside the known rules that the object was initially dismissed as impossible, an artifact in the data. But repeated observations confirmed it, a slow, steady heartbeat from a cosmic corpse that should not be able to produce it. A typical pulsar's rapid spin is powered by the conservation of its original stellar angular momentum, squeezed into a city-sized sphere of pure neutronium. As it spins, its powerful magnetic field acts like a dynamo, converting rotational energy into those focused beams of radiation we detect as pulses. That energy loss causes the pulsar to gradually spin down over millennia. The new object's 22-minute period is so long that, under the standard model, its magnetic dynamo should have shut down eons ago. It should be dark and silent, a cold cinder. Yet here it is, flashing with incredible power. So what is it? Astronomers are grappling with 2 revolutionary possibilities, each rewriting a chapter of stellar evolution. The first is that it is an ultra-long period magnetar. Magnetars are neutron stars with magnetic fields thousands of times stronger than ordinary pulsars, fields so intense they can crack the star's crust and power brilliant X-ray and gamma-ray flares. Perhaps this object represents a new, extremely slow class of magnetar, where the magnetic field itself, twisting and reconnecting, provides the energy for its radio outbursts instead of rapid rotation. The second, even more exotic idea is that it is not a neutron star at all, but a white dwarf pulsar. White dwarfs are the Earth-sized embers of lower mass stars, and they spin much more slowly. A white dwarf with a strong enough magnetic field could, in theory, produce pulsed radio emission, but none have ever been conclusively found. This object could be the first, proving that the pulsar mechanism is not exclusive to neutron stars. Visuals here are essential to grasp the scale of the mystery. A graph comparing pulse periods shows a dramatic outlier, a single day to point far to the right of the tight cluster representing all other known pulsars. An animation could show a typical millisecond pulsar spinning in a blur, its lighthouse beam a frantic strobe, next to this new object rotating with a ponderous, almost stately grace, its beam sweeping around just once in those 22 minutes. The discovery forces a profound question. How many other slow-beating hearts are out there, missed because we were only listening for a rapid pulse? It suggests a hidden population of exotic stellar remnants operating on a different clock entirely, their long, slow rhythms waiting to be heard in the quiet spaces between the ticks of the universe's faster clocks. A slow-beating pulsar defies the expected rhythm of stellar death, but other worlds face a far more dramatic and violent end. Our 10th oddity is a planet so close to its star it is literally evaporating before our eyes. This is WASP-121b, a world known as an ultra-hot Jupiter, and recent observations from the Hubble Space Telescope have revealed its atmosphere in shocking, glowing detail. The data shows something astonishing: the spectral fingerprint of glowing water vapor high in its stratosphere. But this is not the water of Earth's clouds. It is water molecules heated to thousands of degrees, emitting their own light as they are torn apart by the relentless stellar fury. Even more incredible, the same observations found evidence of vaporized metals like iron and magnesium floating high in the planet's air. On Earth, these elements form solid rocks, but on WASP-121b, the heat is so intense they exist as gaseous atoms glowing in the upper atmosphere. The cause of this hellish environment is the planet's crushing proximity to its host star. WASP-121b orbits so close that a full year, one complete trip around its sun, takes just over one Earth day. This locks the planet in a gravitational embrace, with one hemisphere permanently facing the star, the other forever turned to the void of space. The day side is a furnace beyond comprehension, with temperatures soaring above 4,500 degrees Fahrenheit, hot enough to vaporize iron and titanium. The night side, while cooler, is still scorching by any terrestrial standard. This extreme temperature difference, over 2,000 degrees between day and night, drives supersonic winds that scream across the planet's surface, carrying the vaporized metal atoms from the day side to the night. There, they might briefly condense into clouds of liquid gemstones or metallic rain, only to be swept back into the inferno and vaporized once more. To visualize this world requires an artist's concept that captures its doomed majesty. The planet itself is a bloated, puffy gas giant swollen by the heat. Its atmosphere glows with a sickly, reddish-orange light from the superheated metals and water vapor. Most strikingly, stretching away from the star is a faint, comet-like tail, a stream of atmosphere being blasted into space by the star's radiation pressure. This planet is not just hot, it is actively disintegrating, losing mass constantly in a slow-motion stellar wind. WASP-121b presents a stark and beautiful vision of planetary extremes, a laboratory for atmospheric physics where the very air glows with the light of vaporized rock, a world dancing so close to its sun that it is slowly turning to smoke. WASP-121b is a world being stripped bare by its star, a gas giant losing its atmosphere. But what if a planet had its entire gaseous envelope ripped away, leaving only its dense metallic heart exposed? This brings us to a world that defies all expectations of planetary formation, a cosmic heavyweight called TOI-849b. Discovered by NASA test satellite, this planet is classified as a mega-Earth, and the name is no exaggeration. It is about 40 times more massive than our own world, yet it orbits so close to its star that a year lasts only 18 hours. The sheer density of this object is what shatters the mold. Based on its size and mass, astronomers calculated that it must be made almost entirely of rock and metal, with little to no gaseous atmosphere. This presents a profound puzzle. According to our standard models of planet formation, a world that gathers so much mass, especially in the hot inner region of a star system, should have also accumulated a tremendous amount of hydrogen and helium gas during its birth. It should have become a gas giant, a mini Neptune, or even a hot Jupiter. But TOI-849b is not a gas giant. It is a solid behemoth. How did it get so massive without the gas? The leading and most dramatic theory is that we are looking at a planetary corpse, the naked core of a former gas giant. In this scenario, the planet did form normally, first building a massive rocky core many times heavier than Earth. That core's gravity was so strong it successfully pulled in a vast, thick envelope of hydrogen and helium, becoming a Jupiter-like world. But then, something catastrophic happened. Perhaps it migrated too close to its star, and the intense stellar radiation and heat literally blew away the entire gaseous atmosphere over billions of years, like a cosmic sandblaster stripping paint from metal. Alternatively, it could have suffered a violent collision with another giant planet, an impact so titanic that it sheared off the gaseous layers and left only the dense core behind. Visualizing this requires a stark comparison. First, show a scale model of our solar system's rocky planets with tiny Mercury, Venus, Earth, and Mars. Then, introduce TOI-849b as a colossal sphere dwarfing them all, a single rocky world with the mass of all those planets combined. A cutaway diagram is even more revealing. The interior would not look like Earth's layered mantle and core. Instead, it would be an almost uniform mass of incredibly compressed rock, surrounding a central sphere of molten iron and nickel under pressures we can scarcely comprehend. This is not a place with continents or oceans. It is a planetary scale ball bearing, a fragment of a world that once was. Its very existence forces astronomers to reconsider the boundary between rocky planets and gas giants. It proves that under the right, or perhaps terribly wrong, circumstances, a planet can be stripped to its essence, revealing the dense skeleton that lies at the heart of every giant. TOI-849b is a cosmic fossil, a silent testament to the violent histories that can unfold around other stars. That planetary fossil is a world stripped to its core, but some planets exist in a state of gravitational chaos from the very beginning. Our next oddity is a world that defies the simple image of a single sun in the sky, a planet that calls not one but three suns home. This is KOI-5b, a gas giant discovered over a decade ago but nearly forgotten because its signal was so baffling. Recent data from the TESS satellite has finally confirmed its existence, revealing a cosmic ballet of staggering complexity. This planet orbits within a triple star system, a place where the sky would present a spectacle unlike any other. Here is how the dance unfolds. At the center of the action is a close binary pair, star A and star B, locked in a tight mutual orbit. The planet KOI-5b circles only star A, completing a year in about 5 Earth days. But star B is not a distant backdrop. It is a partner in a gravitational tango, whirling around the same central point as the planet's host star. To make the system even more dramatic, a third star, star C, orbits this inner pair from a much greater distance, taking roughly 1,000 years to complete a single loop. This creates a celestial hierarchy, a planet orbiting one star in a binary, which is itself orbited by a distant stellar companion. The mere existence of a stable planet here is a marvel of orbital mechanics. In such a crowded gravitational neighborhood, the competing pulls from multiple massive bodies should, in theory, quickly destabilize a planet's path, either flinging it into deep space or sending it crashing into one of its suns. Yet KOI-5b persists. Its orbit is markedly misaligned, tilted relative to the plane of the binary star's orbit, a clue that it may have been gravitationally kicked and twisted during the system's violent early history. Astronomers believe its survival hinges on a delicate balance. The planet's orbit around star A is close and fast, giving it a strong gravitational bond to its primary host. Meanwhile, the orbit of the binary companion, star B, is wide enough that its disruptive tugs, while significant, occur at a rhythm that does not perfectly resonate with the planet's orbit, preventing a buildup of destabilizing forces over time. Visualizing this demands an animation to untangle the motion. We start with a view of the triple star system, the close binary pair whirling around each other rapidly, with the planet a swift dot tracing its circle around star A. Then we pull back to reveal the slow, grand sweep of the distant third star, star C, tracing a huge ellipse around the entire inner system. The planet's path is not a simple flat circle, but a slightly wobbling ring, its inclination a frozen record of past gravitational encounters. The confirmation of this world solves one mystery but opens another. How did it form in such a chaotic environment? Did it coalesce in place around star A, fighting against the gravitational tides from its stellar siblings, or did it form farther out and migrate inward, its orbit twisted along the way? KOI-5b is a testament to the universe's inventiveness, proving that planets can thrive in places we once thought were hopelessly unstable, a world under 3 suns where every sunrise could be a multiple event. 3 suns create a complex gravitational dance, but the death of a single star can unravel an entire planetary family with terrifying finality. Our 13th oddity is a cosmic autopsy in progress, a system called WD1145+017. Here, astronomers are witnessing the violent end of a world, shredded into a cloud of dust and vapor as it orbits the corpse of its own sun. The star is a white dwarf, the dense, Earth-sized cinder left behind after a sun-like star exhausts its fuel, swells into a red giant and then sheds its outer layers. What remains is a super-hot ember of carbon and oxygen, incredibly dense and gravitationally powerful. Around this dead star, telescopes have detected a telltale signature not of intact planets but of their destruction. The key evidence comes from spectroscopy, the technique of splitting starlight into a rainbow to reveal its chemical fingerprint. When scientists analyzed the light from this white dwarf, they found it was polluted. The pure atmosphere of the star, which should contain only hydrogen or helium, was contaminated with heavy elements like iron, magnesium, silicon, and calcium. These are the building blocks of rock and metal, the ingredients of terrestrial planets. They do not belong in the atmosphere of a white dwarf. Their immense gravity should pull such heavy elements down into the core in a matter of days. The only explanation is a continuous, fresh supply is raining down onto the star from above. The source of this pollution was revealed by watching the star's light over time. It dims in a bizarre, irregular pattern, not the clean dip of a planet but a jagged, sawtooth pattern of fading and brightening. This is the signature of a disintegrating body. Astronomers believe a small, rocky planet, or perhaps a large asteroid, ventured too close to the white dwarf. The star's immense gravity creates such a powerful tidal force that it overcomes the planet's own gravity, literally pulling it apart. The planet is being spaghettified, stretched into a long stream of debris that forms a dusty, elliptical ring around the star. As this stream of fragments crosses our line of sight, it blocks different amounts of starlight, creating that chaotic dimming pattern. Visuals here tell a story of both forensic science and cosmic violence. First, a graph of the star's light curve shows those erratic, jagged dips, a heartbeat of disintegration. Next, a spectrum of the star's light reveals sharp, dark lines at specific wavelengths, each one marking the presence of a foreign metal like iron or silicon in the star's atmosphere. Finally, an artist's impression shows the scene. The white dwarf glows with a fierce blue-white heat at the center. Orbiting it is not a solid sphere, but a long, thin stream of glowing rubble, rocks and dust glowing red-hot as they spiral inexorably inward. This system is a direct glimpse into the far future of our own solar system. In about 5 billion years, our sun will become a red giant, likely engulfing Mercury and Venus and rendering Earth uninhabitable. Eventually, it will shed its outer layers to become a white dwarf. The surviving planets, their orbits possibly destabilized by the star's violent transformation, could then fall inward, meeting the same shredded fate. WD1145+017 is not just a strange sight, it is a prophecy written in starlight and metal, showing us the eventual dramatic end of worlds. That disintegrating world is a slow-motion tragedy, but some cosmic events announce themselves in a single, brilliant flash. For over a decade, one of astronomy's greatest puzzles has been the fast radio burst, an intense blast of radio waves that lasts just milliseconds yet outshines entire galaxies. They came from deep space, their origins completely unknown, sparking theories from colliding neutron stars to alien transmissions. Then, in April of 2020, a detector on Earth picked up a signal that changed everything. This was FRB 20200428, and it did not come from a distant galaxy. It came from inside our own Milky Way. The source was instantly identified, a known magnetar in our galactic backyard called SGR 1935+2154. Magnetars are the universe's ultimate magnets, neutron stars with magnetic fields 1,000 trillion times stronger than Earth's. This particular object was already known for its occasional X-ray grumbles and flares. But on that day, it did something unprecedented. It produced a radio burst so powerful that if it had come from a nearby star, we would have heard it on an ordinary car radio. This was the smoking gun. For the first time, astronomers could point to a specific known object and say, "This is where a fast radio burst came from." The detection was a monumental breakthrough, confirming that at least some of these mysterious flashes are generated by the immense, twisted magnetic fields of these stellar corpses. The likely mechanism is a starquake. A magnetar's crust is under unimaginable strain, locked in a battle between the inward crush of gravity and the outward pressure of the magnetic field. When that crust finally cracks, it releases a cataclysmic shudder, an earthquake on a star. This quake unleashes a storm of particles and energy, shaking the magnetic field lines themselves. As those lines snap and reconnect, they can accelerate particles to near light speed in an instant, producing that brilliant, fleeting pulse of radio waves we detect across the cosmos. Visuals here are key to understanding the discovery's impact. First, a map of the Milky Way galaxy, a spiral disk seen face-on. A point of light flashes in one of the spiral arms, not in the distant halo but within our own stellar neighborhood. Next, we see the actual data, a graph from the Canadian Hydrogen Intensity Mapping Experiment, or CHIME telescope. It shows a single vertical spike rising from a flat line, a stark, solitary blip of immense power lasting only a millisecond. This one image connected a theoretical object to a real phenomenon. Yet, for all its importance, this galactic fast radio burst also presented a mystery. It was noticeably weaker than most of the extragalactic bursts detected from billions of light-years away. If those distant bursts are also from magnetars, they would have to be unimaginably more energetic to be visible across such vast distances. This suggests that while we have solved one piece of the puzzle, magnetars are likely not the only source. There may be multiple cosmic engines capable of producing these flashes, from merging black holes to exotic superconducting strings. The detection within our galaxy was a crucial key, but it may have unlocked a door to a room full of even stranger machines. The galactic fast radio burst gave us a source, but the universe's largest structures are woven from threads we are only beginning to see. Astronomers peering into the deep past have now found one of these threads, a colossal filament of galaxies so immense it has been named the cosmic vine. This is not a random scattering of islands in the void, but a connected highway, a tendril of at least 20 massive galaxies stretching across the early cosmos like a root system through dark soil. Discovered in data from the James Webb Space Telescope, the vine existed when the universe was only about 3 billion years old, a mere quarter of its current age. Its sheer scale and maturity so soon after the Big Bang present a direct challenge to our models of cosmic evolution. We understand that the universe is structured like a vast web, with galaxies clustering along filaments of dark matter that intersect at dense nodes. This cosmic web is the large-scale skeleton of everything, but simulations of this process typically show it taking much longer for such enormous, gravitationally bound structures to assemble. The cosmic vine suggests the early universe was a faster, more efficient builder than we thought. How did 20 giant galaxies, each a bustling metropolis of billions of stars, manage to line up and link together in such a relatively short cosmic time? The leading hypothesis points to the overwhelming influence of those dark matter filaments. In the primordial universe, slightly denser regions of dark matter acted as seeds, their gravity pulling in ordinary gas. The cosmic vine likely traces one of these primordial rivers of invisible mass, a pre-existing highway in the dark. Gas flowing along this dark matter channel would have cooled and fragmented, triggering furious waves of star formation up and down its length, essentially planting galaxies at intervals like beads on a string. The galaxies within the vine are not just neighbors, they are interacting, their gravitational pulls stirring the gas around them and influencing each other's growth in a chain reaction of creation. To visualize this discovery requires two powerful images side by side. First, the deep field view from James Webb, a region of sky that looks like a starry void to other telescopes, is revealed as a crowded tapestry of faint red smudges. Overlaying this image, a highlighted line connects a string of these smudges, tracing the subtle, vine-like structure across the frame. Next to it, a supercomputer simulation of the cosmic web shows the universe as a shimmering network of light with glowing filaments connecting bright knots. The vine is a real-world snapshot of one of those glowing threads caught in its youth. This structure forces a profound question. Were the first galaxies born in isolation, or were they destined from the beginning to be part of these immense connecting vines? Finding this single thread implies the early cosmos was already richly structured, its web taking shape at a breathtaking pace, weaving the first great cities of stars into a connected empire long before our own galaxy was fully formed. While the cosmic vine reveals the grand architecture of the early universe, our own galactic center hides stars that act like cosmic chimneys. Astronomers have discovered a bizarre new class of elderly stars, nicknamed old smokers, lurking in the crowded heart of the Milky Way. These are not brilliant blue youngsters, but ancient red giants, stars in their final stages of life. For decades, they remained virtually invisible, hidden in plain sight by the dense clouds of dust that shroud the galactic core. What makes them odd is their behavior. They will sit quietly for years, then, without warning, they begin to dim dramatically. As they fade, they eject enormous clouds of dark, smoke-like dust, obscuring their own light for months or even years before clearing again. It is as if these old stars are having periodic coughing fits, expelling sooty material into space around them. The discovery came from a decade-long survey that monitored hundreds of millions of stars, specifically looking for changes in brightness. Among the expected variable stars and nova, this strange, slow-dimming pattern stood out, revealing an entire population of previously overlooked giants. Visualizing them requires a shift to the infrared. In visible light, the galactic center is a murky wall of darkness, but infrared light pierces the dust, revealing a stunning, crowded metropolis of stars swirling around the central supermassive black hole. Within this brilliant throng, time-lapse sequences show specific points of red light gradually fading, as if a veil is being drawn over them before slowly brightening once more. This smoke is not mere soot, it is stardust in the most literal sense, and it may solve a long-standing cosmic mystery. These heavy elements, forged in the furnaces of previous stellar generations, are the building blocks of rocky planets and life itself. For years, astronomers have wondered how these elements are distributed so evenly throughout the galaxy. The violent explosions of supernova can blast material far and wide, but they are rare and chaotic. The old smokers offer a gentler, more continuous delivery system. Each time one of these stars has a smoky episode, it releases a fresh batch of processed elements, carbon, oxygen, iron, and more directly into the interstellar medium of the galactic core. From there, the galaxy's rotation and dynamics can spread these enriched materials outward. These aging stars, once thought to be quiet retirees, are now revealed as key players in the galactic ecosystem, puffing out the very ingredients for future worlds with every slow, dusty exhalation. Their discovery reminds us that even the oldest actors on the cosmic stage can have surprising, vital roles yet to play. That gentle dust from the old smokers enriches the galaxy, but the death of a star can sculpt space into shapes of breathtaking cold. For years, the Boomerang Nebula was known as the coldest natural place we had ever found. Images from the Hubble Space Telescope presented a stunning, ethereal vision, a glowing bow tie or butterfly shape with two distinct lobes spreading outward. This seemed to fit a classic model of stellar death, where a dying star ejects its outer layers in two opposing jets, creating a bipolar nebula. But new, profoundly detailed observations from the Atacama Large Millimeter Array, or Oumuamua, have shattered that beautiful illusion. The nebula is not a bow tie at all. It is almost perfectly spherical, a vast, nearly round cloud of expanding gas. The Hubble image was a trick of light and perspective, a two-dimensional view of a far more complex three-dimensional object. The Oumuamua data, which maps the distribution and velocity of molecules in the cold gas, allowed astronomers to construct a true three-dimensional model. What they found was a star in its final throes, but its death is not a neat two-directional event. Instead, the star is expelling its atmosphere in a frantic, nearly spherical outburst, but at wildly different speeds. The material expanding along our line of sight, toward and away from us, is moving much faster and has cleared out more space, creating the illusion of empty lobes. The slower moving material around the star's equator forms a dense, dusty waste, which we see in silhouette as the dark band in the Hubble image, completing the bow tie mirage. This new shape has dramatic implications. A perfectly spherical outflow suggests the dying star's magnetic field, which often channels material into jets, may be surprisingly weak or disordered here. Instead, the star might be rotating so rapidly or be in such a turbulent binary interaction that it is flinging material out in all directions like a spinning garden sprinkler. The intense cold, just 1 degree above absolute zero, is a clue to this violent process. The gas is expanding so rapidly that it cools adiabatically, like the chill you feel from air rushing out of a spray can. To grasp this transformation, a side-by-side comparison is essential. First, show the iconic Hubble photograph, that elegant, ghostly bow tie of blue and white against the black. It is a work of cosmic art. Then, reveal the new Oumuamua three-dimensional model, a simple, almost plain sphere, with color coding to show the velocity of the gas, the reds and blues indicating the faster material shooting out toward us and away. The difference is not just a correction, it is a revolution in understanding. The nebula is not a carefully sculpted butterfly, but the chaotic, explosive last breath of a star freezing itself in the process. It reminds us that the universe often presents a beautiful facade, while the deeper, hidden truth is a story of far greater violence and chaos. The Boomerang Nebula's hidden shape reveals how perspective can deceive, but sometimes the truth is hidden in plain sight within a familiar cosmic landmark. For centuries, the globular cluster Omega Centauri has been a jewel of the southern sky, a dense sphere of millions of stars orbiting our galaxy as a single, ancient unit. Through a backyard telescope, it appears as a fuzzy patch of light, a snow globe of ancient suns. But the Hubble Space Telescope has peered into its very heart, and the motion of stars there tells a story of a hidden monster, a black hole of a type astronomers have hunted for decades. This is the intermediate mass black hole, the crucial missing link in the black hole family tree. We know of two main classes, stellar mass black holes up to about 100 times the mass of our Sun, form from the collapse of giant stars. And at the other extreme, supermassive black holes, millions to billions of solar masses, lurk in the centers of galaxies. The gap between them has been a theoretical puzzle. How do the small ones grow into the giants? There must be a middle step, black holes weighing thousands of solar masses. Omega Centauri appears to hold one. Hubble's precise measurements focused on stars whipping around the cluster's core. Just as planets orbit the Sun faster when they are closer, the speed of these stars reveals the mass of whatever they are circling. The data showed several stars moving at velocities far too high to be explained by the combined gravity of the visible stars alone. Something invisible and incredibly dense, with a mass of at least 8,200 suns, must be holding them in such a tight, swift dance. Visualizing this discovery requires two powerful perspectives. First, a wide-field image of Omega Centauri itself, a breathtaking globe of countless pinpoint stars against the velvet black of space. Then we zoom in dramatically to the core, where Hubble's data transforms into an animated map. We see the predicted orbits of several specific stars traced out over time, their paths curving sharply around an empty central point. Their speed is the giveaway, a silent but definitive signature of a gravitational anchor we cannot see. This intermediate mass black hole could be a fossil from the cluster's violent past. Omega Centauri is unusual, so large and complex that many astronomers believe it is not a true globular cluster at all, but the stripped core of a small galaxy that was devoured by the Milky Way long ago. If that is true, this black hole could be the dormant remnant of that galaxy's central engine, a relic of a former sovereignty now swallowed into our own. Its existence provides a direct clue to how the behemoths in galactic centers might have first formed, growing from seeds like this one through eons of mergers and feasts. Finding it in such a familiar place is a reminder that some of the universe's greatest secrets are not in the distant voids, but in the crowded neighborhoods we thought we knew. The search for a monster in Omega Centauri's heart reveals how dark matter's signature is written in stellar motion, but one galaxy seemed to defy that cosmic law entirely. This is the profound puzzle of NGC 1052DF2, a galaxy that sparked a firestorm when initial observations claimed it contained virtually no dark matter at all. That announcement was revolutionary because dark matter is not just an add-on, it is the fundamental scaffold for all large structures in the universe. According to our most successful models, a galaxy of this size, a diffuse collection of stars, simply cannot hold itself together without the immense gravitational glue of an invisible dark matter halo. Its existence would have been like finding a towering skyscraper built with no steel frame, standing against the wind through sheer luck. The original measurements, based on the apparent brightness and motion of its stars, suggested a galaxy made almost entirely of ordinary matter, a cosmic heresy that threatened to upend decades of astrophysics. The debate that followed was fierce and necessary, a perfect example of science self-correcting. The central point of contention turned out to be one of the most fundamental yet tricky numbers in astronomy: distance. To weigh a galaxy, you need to know how far away it is. The mass inferred from the motion of its stars, the dynamical mass, depends on that distance. So does the mass you estimate from its total starlight, the luminous mass. If you get the distance wrong, both calculations fall apart. The latest research, using more precise methods with the Hubble Space Telescope, suggests the initial distance to NGC 1052DF2 may have been significantly overestimated. If the galaxy is actually closer to us than we thought, then everything changes. Its stars would be intrinsically fainter, meaning the galaxy contains less ordinary matter than first calculated. Simultaneously, the observed motions of its stars would imply a lower total mass as well. Crucially, the gap between these two numbers, the space where dark matter should reside, might shrink dramatically or even vanish. The galaxy could shift from being a dark matter-free anomaly to a more conventional, if still unusual, object where the dark matter content is simply much lower than average. Visuals are critical to untangling this controversy. A side-by-side graphic is powerful. On one side, show the original, larger distance estimate. The galaxy appears bright. Its stars imply high luminous mass, but their slow motion suggests low total mass, leaving a huge deficit where dark matter should be. On the other side, show the new, closer distance. The galaxy dims, its luminous mass estimate drops, and the recalibrated stellar motions now point to a much lower total mass, with the two values aligning more closely. The gap, the missing dark matter, closes. This debate is far more than academic. It strikes at the validity of our entire framework for understanding the cosmos. If a galaxy truly lacks dark matter, it means galaxy formation is possible through pathways we have never considered, and our theories of dark matter itself might need revision. If, however, the anomaly vanishes with better data, it reinforces the incredible power and consistency of the dark matter model. NGC 1052DF2 stands as a testament to a fundamental truth. In our quest to understand the universe's greatest oddities, the first mystery we must often solve is simply how far away they really are. The distance to a galaxy is a fundamental measurement that can change everything we think we know, but some of the most exciting discoveries are not about galaxies at all, but about the moons that might orbit distant worlds. For decades, we have catalogued thousands of exoplanets, but finding an exomoon, a moon around one of those planets, has remained an elusive frontier. That is, until astronomers pointed the Hubble Space Telescope at a gas giant called Kepler 1625b. The data revealed a tantalizing, yet deeply controversial, hint of a companion, a candidate now known as Kepler 1625bi. The method of detection is a masterclass in precision. As the planet passes in front of its star, it causes a predictable dip in starlight, a transit. But the Hubble data showed something extra. Just before the main planetary dip, there was a smaller, distinct decrease in brightness. Then, after the planet's transit ended, another slight dimming occurred. It was as if a smaller object was leading the planet and then trailing it like a moon in a slow orbital dance. Even more compelling, the planet itself did not transit exactly on time. Its arrival was delayed, a phenomenon called a transit timing variation. This suggested the planet was wobbling slightly in its orbit, its path gently tugged by the gravitational pull of a massive, unseen moon. The evidence painted a picture of a true giant. The candidate moon, based on the depth of those extra dips, appeared to be roughly the size of Neptune. Imagine a gas giant planet several times the mass of Jupiter, accompanied by a moon that is itself a gas world, a binary planet system dancing around a distant sun. An artist's concept brings this staggering scale to life. The massive, banded primary planet dominates the view, with its enormous, cloudy companion hanging in the sky, a world that would dwarf every moon in our own solar system. Yet, despite the initial excitement, follow-up observations have been frustratingly inconclusive. Other telescopes, including a later Hubble program, failed to definitively confirm the signal. The extra dips in starlight were subtle, buried in noise, and some analyses suggest they could be artifacts of the telescope's instrumentation or the complex process of subtracting the star's own natural flicker. The scientific community remains divided, with some teams standing by the moon interpretation and others attributing the data to stellar activity or systematic error. This controversy highlights the immense challenge of the hunt. An exomoon signal is vanishingly small, a faint whisper superimposed on the already subtle signal of a planet. It requires not just precision, but also luck, a perfect alignment, and an extraordinarily large moon to even have a chance of being detected from over 4,000 light-years away. The quest for Kepler 1625bi is a story of how science operates at its very limits, where a breathtaking possibility hangs in the balance, awaiting the next generation of telescopes to either confirm a new class of world or consign it to the realm of tantalizing but unproven cosmic ghosts. The search for distant moons pushes our telescopes to their absolute limits, but sometimes the universe places its strangest discoveries right in front of us, in wavelengths our eyes can never see. In recent wide-field radio surveys, astronomers have stumbled upon something that defies immediate classification: enormous, faint rings in the sky they have named odd radio circles. These ORCs are exactly that, perfect circular shells of radio emission, some so vast they could swallow entire galaxies. The most baffling part is their invisibility when you look at the same patch of sky with optical, infrared, or X-ray telescopes. There is absolutely nothing there. It is as if someone has drawn ghostly circles on the cosmic canvas with a pen that only radio antennas can read. The discovery was a pure accident found in data from the Australian Square Kilometre Array Pathfinder, a telescope designed to map the sky in radio waves with unprecedented speed and sensitivity. These circles are not small, they span hundreds of thousands of light years across, and they are incredibly faint, which is why they were missed until now. Their perfect symmetry is a clue, suggesting a single, explosive event or a spherical shockwave expanding uniformly through space. But what could create such a titanic yet invisible structure? The leading natural theory points to a galactic wind, a torrent of particles blown out from a starburst galaxy experiencing a frenzy of star birth. If such a wind were to collide with an ancient shell of gas left over from a previous eruption, it could create a spherical shockwave that lights up in radio waves. Another idea is that they are the aftermath of a colossal merger between two supermassive black holes, an event so energetic it sends a spherical tsunami of radio emission rippling through the intergalactic medium. Yet the sheer perfection and isolation of these circles have sparked more exotic possibilities. Could they be the throats of wormholes, theoretical tunnels through space-time, their mouths glowing with the radiation of particles caught in their extreme gravitational fields? Or perhaps they are the imprint of a bubble blown by a powerful, yet brief, flash of energy from an unknown source, a cosmic echo frozen in radio light. The truth is, no single theory fits all the observations perfectly, and that is the hallmark of a genuine cosmic oddity. To grasp their strangeness, a side-by-side comparison is essential. On one side, a radio telescope image shows a crisp, ethereal ring, a pale donut of emission hanging in the void. On the other, an optical image of the exact same coordinates reveals only a few faint, unrelated stars, a blank canvas where the radio circle blazes. This disconnect between what we see and what we sense with different tools is a profound reminder of how much of the universe operates in channels beyond our natural perception. The odd radio circles are not just objects, they are questions made manifest, silent, giant halos asking us to decipher the story of their violent, invisible birth. The ghostly perfection of odd radio circles asks us to consider what else we might be missing in the familiar. While those structures are invisible to our eyes, another world reveals its strangeness through the very colors of its atmosphere. On a scorching gas giant named HATP-7b, scientists have found evidence for a weather forecast that sounds like a fantasy, clouds that might be made of crushed jewels and a rain of gemstones. This planet is another ultra-hot Jupiter, orbiting so close to its star that its year lasts just over 2 Earth days. This proximity creates a staggering temperature divide, a permanent, searing day side and a somewhat cooler, but still brutally hot night side. Observations from the Kepler Space Telescope did not just find this world, they caught its atmosphere in the act of dramatic change. By measuring the subtle variations in the planet's total brightness as it orbited, astronomers detected bright spots in its clouds that were shifting position over time. These moving patches of reflected starlight signaled colossal storms, driven by the extreme temperature difference between the two hemispheres. The heat on the day side is so intense, likely exceeding 4,000 degrees Fahrenheit, that it vaporizes minerals that would be solid rock on Earth. Elements like aluminum and oxygen are ripped apart and swept up into the atmosphere. Here, the physics becomes almost poetic. the planet's fierce, supersonic winds racing from the hot day side to the slightly cooler night side carry these vaporized ingredients. As the air masses cross into the darkness, they cool just enough for condensation to begin. But this is not the condensation of water vapor. In this furnace, aluminum and oxygen can condense directly into clouds of corundum, the very mineral that, with different trace impurities, forms rubies and sapphires on Earth. Imagine, then, the skies of this alien world. They would not be soft and white, but potentially shimmering with opaque, reflective clouds of microscopic gem dust glittering with reflected starlight. And what goes up must eventually come down. Under the immense gravity of this giant world, these mineral droplets would grow heavy and fall. The precipitation on HATP-7b could literally be a rain of liquid rubies and sapphires, a sparkling downpour that evaporates back into vapor long before reaching any solid surface, returning to the day side to begin the cycle anew. An artist's depiction brings this impossible beauty to life. The planet's limb curved against the black of space, its upper atmosphere streaked with high, glittering clouds of crimson and deep blue. Below, in the deeper atmospheric layers, streaks of gleaming precipitation fall through bands of violent storm clouds, a permanent, violent storm where the sky itself turns precious stone into weather. This gemstone rain is more than just a captivating idea. It is a direct clue to the complex chemistry and fluid dynamics of worlds far beyond our own, proving that the universe's creativity extends to crafting storms of breathtaking and literal brilliance. A rain of gemstones falls on a distant world, but some stars are forged in explosions that send them fleeing across the galaxy. This is the story of a true cosmic runaway, a hypervelocity star known as J0927. Using the precise stellar map from the Gaia spacecraft, astronomers have traced this star's frantic path, and its trajectory points directly back to a violent birth. It is now hurtling through the Milky Way at over 2 million miles per hour, a speed so great it will eventually escape the galaxy's gravitational pull entirely, condemned to wander the intergalactic void. The only force in nature capable of giving a star such a kick is a supernova. The most likely story begins with two stars, a binary pair locked in a close orbit. One was more massive, destined to burn through its fuel quickly and die young. When that star finally exhausted its nuclear furnace, its core collapsed in a cataclysm, triggering a supernova explosion of unimaginable power. In a normal supernova, the explosion is symmetric, blasting the star's outer layers into space while leaving behind a neutron star or black hole. But in a binary system, the geometry changes everything. If the explosion is slightly lopsided, or if the sudden loss of mass from one star instantly breaks the gravitational bond, the surviving companion can be flung away like a stone from a sling. This is what scientists believe happened to J0927. The supernova did not just destroy one star, it weaponized the other, converting the energy of stellar death into pure unidirectional motion. Visualizing this requires a dynamic sequence. First, we see the binary pair, two stars orbiting a common center of gravity in the galactic disk. The more massive star swells into a red giant, then its core collapses. The screen flashes white with the supernova's shockwave. In the aftermath, a rapidly spinning neutron star or a silent black hole remains where the giant once was. But its companion is no longer in orbit. The explosion has imparted such a tremendous, asymmetric kick that the surviving star is now a bullet, racing out of the debris cloud on a trajectory that will carry it from the galaxy forever. The Gaia data provides the forensic evidence, plotting the star's current position and velocity, then drawing a line backward through time. That line points directly to a region in the galactic disk where young, massive stars are born and die, the perfect stellar nursery for such a dramatic event. This hypervelocity star is more than just a curiosity. It is a tracer bullet illuminating the hidden forces of some of the universe's most energetic explosions. Its lonely journey began in an instant of shared destruction, a partnership severed by fire, leaving one member to carry the momentum of both into the endless dark. A star flung from the galaxy by a supernova is a solitary escapee, but some of the smallest galaxies in our neighborhood appear to be hiding giants of their own. This oddity takes us to the dwarf spheroidal galaxy Leo I, a faint, wispy satellite of the Milky Way so small and diffuse it was once thought to be little more than a loose cloud of ancient stars. Recent measurements of stellar motions near its core, however, have revealed a gravitational signature that is nothing short of shocking. Leo I appears to host a supermassive black hole nearly as massive as Sagittarius, a star, the monster at the heart of our own vast Milky Way. The numbers defy all expectation. The Milky Way contains hundreds of billions of stars, while Leo I holds only a few tens of millions. Our galaxy is a majestic spiral spanning over 100,000 light-years. Leo I is a faint, irregular blob perhaps 2,000 light-years across. According to the established rules, the mass of a central black hole should scale with the mass of its host galaxy's central bulge. A tiny galaxy should have a tiny black hole or none at all. Leo I's black hole, with a mass estimated at around 3 million suns, shatters that rule completely. A powerful visual comparison makes the absurdity clear. A side-by-side graphic shows the two galaxies to scale. The Milky Way is a sprawling, brilliant pinwheel. Nestled beside it, Leo I is a faint smudge, a mere speck of light. Then we zoom into their centers. Two dots appear representing the central black holes. Astonishingly, they are almost the same size. The giant resides in the dwarf. This discovery forces a radical rethinking of the relationship between galaxies and their central black holes. How did such a small galaxy acquire such a massive anchor? One compelling theory is that Leo I is not what it seems. It may be the stripped remnant of a much larger galaxy that ventured too close to the Milky Way long ago. Over eons, our galaxy's immense gravity could have torn away the vast majority of Leo I's stars and dark matter, leaving behind only its dense core and the indestructible black hole at its center. In this scenario, the black hole is not overgrown for its current home. The home has been dramatically downsized around it. Another possibility is that black holes can grow efficiently even in small galaxies, perhaps through direct collapse of giant gas clouds in the early universe, forming massive seeds that then dictate the growth of the galaxy around them rather than the other way around. The hidden giant in Leo I whispers a story of either a dramatic past encounter or a fundamental flaw in our understanding of cosmic growth, proving that sometimes the smallest packages can contain the most disproportionately large surprises. That hidden giant in a dwarf galaxy redefines scale, but some planets achieve a different kind of impossibility, a world so light it could float on water. WASP 107b is an exoplanet that defies the very categories we use to describe worlds. It has the mass of Neptune, a planet we think of as a dense, compact ice giant. Yet its physical size is closer to that of Jupiter, the solar system's bloated king. This combination creates a density so astonishingly low that scientists compare it to styrofoam. If you could find an ocean large enough, this entire planet would bob on the surface like a cosmic beach ball. The secret to this impossible fluffiness lies in its atmosphere, a vast, puffy envelope of hydrogen and helium that extends thousands of miles above a surprisingly small core. Recent observations with the James Webb Space Telescope have peered into this hazy shroud, identifying water vapor and sulfur dioxide, and confirming the atmosphere's extended, diffuse nature. This presents a direct challenge to the standard core accretion model of planet formation. In that model, a planet first builds a solid core of rock and ice. Once that core reaches a critical mass about 10 times that of Earth, its gravity becomes strong enough to rapidly pull in huge amounts of gas from the surrounding protoplanetary disk, forming a thick atmosphere. For WASP-107b, the math does not work. Its core is estimated to be no more than 4 times the mass of Earth, far below that theoretical threshold. It simply should not have been able to grab and hold onto such an immense, fluffy atmosphere. So how did it become so inflated? The answer likely involves a dramatic migration and a generous stellar host. The planet orbits extremely close to a star that is slightly cooler and less massive than our Sun. Scientists believe WASP-107b formed much farther out in its system, beyond the frost line where icy materials are plentiful, allowing it to build its core. Then it migrated inward to its current scorching orbit. The intense heat from its nearby star pumps enormous thermal energy into the planet's atmosphere, causing it to swell up like a hot air balloon. Furthermore, because the star is relatively gentle, its stellar winds are less forceful, allowing the planet's tenuous atmosphere to persist without being completely stripped away. A cutaway diagram reveals the true oddity of its structure. At the center, a small, dense core of rock and ice comparable to a super-Earth. Surrounding it, not the deep, compressed layers of a typical gas giant, but an immensely thick, gradually thinning haze of gases that comprises most of the planet's volume. This is not a tightly bound world, but a loosely held cloud with a planet at its heart. WASP-107b stands as a lesson in planetary diversity, proving that worlds can inflate to fantastical dimensions under the right stellar spotlight, their very puffiness a clue to a violent journey across their solar system. The fluffiest planets and hidden giants reveal the diversity of worlds, but some of the strangest lights in our solar system shine in energies invisible to our eyes. Astronomers using the Chandra X-ray Observatory have made a startling discovery at the ice giant Uranus. They have detected X-rays emanating from the planet. This marks the first time such high-energy radiation has been seen from this distant, tilted world, and the source is a compelling puzzle. On Earth, the beautiful northern and southern lights are a spectacle of visible light caused by charged particles from the Sun interacting with our magnetic field. Uranus also has auroras, but its conditions are profoundly alien. The planet rotates on its side, its magnetic field is oddly offset and twisted, and it is so far from the Sun that the solar wind is much weaker. The detected X-rays likely come from auroral processes, but the mechanism is not clear. One possibility is that the X-rays are produced by charged particles from the solar wind, even at that great distance, being accelerated by Uranus's bizarre magnetic field and colliding with atoms in its atmosphere. Another, more intriguing idea points homeward to Uranus's own system. The planet's rings are dark and faint, but they are composed of countless small particles. When charged particles from the Sun or from Uranus's radiation belt strike these ring particles, they could cause them to fluoresce, emitting X-rays in a process similar to how medical X-ray machines work. Studying these X-ray auroras is far more than cataloging a curiosity. Ice giants like Uranus and Neptune represent the most common class of planet discovered around other stars, yet they are the least understood in our own solar system. Their internal structure, magnetic dynamos, and atmospheric dynamics are shrouded in mystery. The X-ray emissions act as a remote diagnostic tool, a way to probe the strength and configuration of Uranus's magnetic field, the composition of its upper atmosphere, and even the density of particles in its environment, all from across the solar system. To visualize this hidden layer of activity, a composite image is powerful. Begin with a classic optical view of Uranus from the Voyager 2 flyby or Hubble, showing its serene, featureless blue-green disk and its faint vertical rings. Then overlay the data from Chandra. Where the optical image shows calm, the X-ray data reveals glowing hotspots at the poles, and perhaps even a faint, ethereal glow along the plane of the rings. This combined view unveils an energetic Uranus, a world crackling with invisible light, its quiet facade hiding a storm of high-energy physics. This discovery reminds us that every planet is a multi-layered story, and sometimes the most revealing chapters are written in wavelengths we were never born to see. While Uranus crackles with X-rays from within, at the very frontier of our solar system, the Sun's influence weaves a different kind of invisible tapestry. The twin Voyager probes, humanity's most distant emissaries, have mapped the final boundary where the solar wind meets the galactic void, and there they found a strange and bustling corridor. Scientists call it the magnetic highway, a turbulent region at the very edge of the Sun's protective bubble, the heliosphere. This is not a solid wall, but a dynamic frontier where the Sun's magnetic field lines, stretched thin by the outgoing solar wind, suddenly reconnect with the magnetic field of interstellar space itself. That reconnection opens a literal highway, allowing charged particles from inside our solar bubble to stream outward, and energetic cosmic rays from the galaxy to pour inward. For the first time, we could observe the direct exchange of material between our star and the wider Milky Way. Before Voyager 1 crossed this threshold, many imagined the heliopause as a relatively smooth, comet-shaped boundary, defined solely by the pressure balance between the solar wind and the interstellar medium. The discovery of the magnetic highway revealed a far more complex and porous interface. It showed that magnetic forces, not just simple pressure, dominate the structure of our cosmic neighborhood's outer skin. The highway region is marked by intense turbulence, a kind of magnetic froth where field lines break and reconnect in a chaotic dance, creating temporary channels for particle flow. To visualize this invisible frontier, a diagram is essential. Picture the heliosphere not as a smooth bullet shape, but as a lumpy, magnetic bubble moving through the galactic medium. The nose, where the solar system plows forward, is compressed. The tail stretches far behind. Now, highlight a zone just inside the boundary layer, particularly along the flanks. This is the magnetic highway, a shimmering, interconnected network of pathways where the Sun's magnetic influence handshakes with the galaxies. This discovery fundamentally changed our understanding of the solar system's shape and our place within it. We do not reside in an isolated, pristine bubble. We live in a dynamic structure that constantly interacts with the galaxy, breathing particles in and out through magnetic portals we are only beginning to map. The Voyagers, silent and cold but still reporting, taught us that even at the edge of the known, the universe is woven together by forces we cannot see, a silent exchange along a highway built of magnetism. The magnetic highway at our solar system's edge shows how porous boundaries can be, but entire worlds can be built from that same principle of extreme fluffiness. In the Kepler 51 system, astronomers have found not one, but 3 planets that defy all conventional density. These are the super puffs, worlds with the mass of a few Earths inflated to sizes rivaling Jupiter, giving them an average density lower than cotton candy. If you could place them in a cosmic ocean, they would not just float, they would bob like absurdly giant, insubstantial beach balls. The system itself is remarkably young, only about 500 million years old, a mere toddler compared to our 4.5 billion-year-old solar system. This youth is the critical clue to their bizarre nature. The leading theory paints a picture of planets caught in a fleeting, bloated adolescence. They likely formed far from their star, in the cold outer regions where they could accumulate massive, primordial atmospheres of hydrogen and helium, much like Jupiter did. But then, something pulled them inward to their current close orbits. Now, bathed in intense stellar radiation, their vast gaseous envelopes are heating up and expanding, puffing out to incredible dimensions. These are not solid worlds with thin skies. They are overwhelmingly atmosphere, with perhaps a small rocky core buried deep within a hazy shroud thousands of miles thick. Observations with the Hubble Space Telescope support this, revealing that their atmospheres are not clear, but filled with a high-altitude haze of tiny particles. likely photochemical smog created as the star's light breaks apart methane and other molecules. This haze acts like a thermal blanket, trapping heat and contributing to the extreme puffiness, while also obscuring our view of the deeper atmospheric layers. An artist's view makes their strangeness stunningly clear. The scene shows a reddish dwarf star at the center. Orbiting remarkably close are three colossal, softly glowing orbs. They are not banded and structured like Jupiter, but appear as smooth, hazy spheres in pastel shades of pink, peach, and cream, their edges fuzzy and indistinct against the black of space. A scale comparison is essential. Place Jupiter next to one of these super puffs. While Jupiter is a compact, powerful-looking sphere, the Kepler-51 planet would loom far larger, a ghostly giant with a faint, ethereal presence. Their current state is not permanent, however. This is a race against time. The same stellar heat that inflates them is also slowly but relentlessly stripping those immense atmospheres away. Over the next few billion years, these cotton candy worlds may shed their fluffy cloaks entirely, leaving behind exposed, rocky cores much closer to their star, transformed from puffy giants into scorched, barren remnants. They offer us a rare snapshot of planetary evolution in its most extreme and vulnerable phase, a glimpse of what happens when a world is moved too close to the fire before it has fully grown up. The super puffs are worlds in their fleeting youth, but the final stages of a star's life can lay bare the entire history of its planetary family. The white dwarf known as G238-44 is performing a cosmic autopsy, and the results are gruesomely detailed. By analyzing the starlight with spectroscopy, astronomers have found its atmosphere is polluted with a shocking variety of elements. There is iron, magnesium, silicon, and oxygen, the clear fingerprints of rocky, Earth-like planets and asteroids. But mixed in with those are the signatures of nitrogen, carbon, and even volatile ices. This is the crucial detail. The white dwarf is not just consuming dry, rocky debris. It is also feasting on material rich in water ice and other frozen compounds, the very stuff of distant comets. This means the star is simultaneously tearing apart objects from two radically different regions of its former planetary system. It is as if our Sun, after becoming a white dwarf, began devouring both the rocky asteroids of the inner solar system and the icy comets of the distant Kuiper belt all at the same time. The sheer breadth of this celestial meal is unprecedented. For a white dwarf to show such a mixed diet implies the gravitational chaos around it is extraordinarily violent. A single, unfortunate asteroid or comet could not explain it. Instead, the star's immense gravity appears to have destabilized the orbits of countless bodies across a vast swath of space, sending a relentless hailstorm of both rock and ice spiraling inward to their doom. An artist's impression captures this chaotic final act. The white dwarf glows with a fierce, blue-white intensity at the center of the scene, but it is not serene. Across its surface, brilliant flashes mark the impacts of disintegrating asteroids, while fainter, icy comets streak in from the darkness, their tails glowing as they vaporize in the intense heat. A faint, elliptical disk of glowing dust and debris, the remains of countless shattered worlds, encircles the star like a ring of cosmic ash. This single, polluted star is a treasure trove for planetary scientists. By measuring the exact ratios of elements in its atmosphere, they can reconstruct the bulk composition of the planets that once orbited it. They can ask, did those alien asteroids have the same iron-to-silicon ratio as rocks in our own solar system? Was the water ice in those comets chemically similar to what fills our oceans? G238-44 offers a direct, albeit destructive, way to perform a chemical census of an entire planetary system, something impossible to do for intact systems light years away. It tells us that systems with distinct zones for rocky and icy bodies, just like our own, may be common. and it reveals a sobering prophecy that the serene architecture of a solar system can, in its final chapter, dissolve into a chaotic rain of fire and ice upon the corpse of its star. White dwarfs perform autopsies on their own planetary systems, but to understand the fate of the entire cosmos, we must map a force that works on the grandest scale of all. Our final oddity is not a single object, but a shadow cast across the universe, a detailed chart of the influence of dark energy. After years of painstaking observation, the Dark Energy Survey has released its most comprehensive map yet, constructed from the precise positions and shapes of hundreds of millions of galaxies. This monumental effort reveals the subtle imprint of a force that is not just holding the universe together, but actively tearing it apart. The data confirms with unprecedented precision that the expansion of the cosmos is accelerating. This is not a gentle drift, but a runaway process driven by dark energy, a repulsive force inherent to the fabric of space itself. The latest findings tighten the constraints on what this mysterious energy could be. It behaves almost exactly like the cosmological constant, a uniform energy density that Einstein once proposed and then discarded. This suggests dark energy is not a weakening field or a decaying particle, but a permanent, unchanging feature of empty space. Yet, there are tantalizing hints in the data that it might not be perfectly constant. Extremely subtle variations in how the acceleration has changed over billions of years could point toward a more dynamic form of energy, one that evolves. To visualize this invisible driver, the survey produces a map of staggering beauty and scale. The recommended visualization is not a simple snapshot, but a three-dimensional model of the cosmic web. You see the universe not as a scattering of stars, but as a vast, intricate lattice. Bright knots and filaments where galaxies cluster along rivers of dark matter glow against an inky black background. But the true story is told by the empty spaces. Between these luminous threads are immense, spherical voids, regions of profound nothingness that span hundreds of millions of light years. These voids are not accidents, they are the primary architecture of the cosmos, and they are growing. Dark energy acts as a kind of cosmic anti-gravity within these empty regions, pushing their boundaries outward and accelerating the expansion of the universe itself. The map shows this in motion, the web stretching, the void swelling, the distances between galaxy clusters increasing at a rate that will only grow with time. This final oddity reframes our entire cosmic story. We live in a universe where the dominant force is not gravity's pull, but a relentless push from the emptiness between the stars. The detailed map from the Dark Energy Survey is our best chart yet for this accelerating voyage into an ever more isolated future, a future written not in starlight but in the silent, expanding dark. These 30 oddities, from the frigid shadow on Jupiter to the dark energy stretching the cosmos, form a tapestry of cosmic bewilderment. Each one, whether a planet of gemstone rain or a galaxy with no stars, represents a crack in our understanding, a place where the universe whispers that our rules are merely suggestions. They teach us that scale is no barrier to strangeness, from the millisecond heartbeat of a black hole to the billion-year growth of a cosmic vine. Every new observation, every flicker of unexpected light, is a question posed directly to us, challenging the very frameworks we use to make sense of reality. The true revelation is not any single object, but the collective message they broadcast. The universe is fundamentally, gloriously, and persistently weirder than our boldest science fiction. It is a realm where monsters hide in dwarf galaxies, where stars smoke like chimneys, and where the emptiest voids hold the greatest power. This journey through the odd is a reminder that exploration is far from over. It is accelerating, fueled by telescopes that see in every wavelength and probes that push into uncharted frontiers. So, as we close this catalogue of cosmic curiosities, we turn the question to you. Which of these 30 oddities reshaped your view of reality the most? Was it the runaway black hole seeding stars, the phantom galaxy of pure dark matter, or the silent, accelerating visitor from another star? Let us know in the comments below, and if you are hungry for more journeys to the edges of understanding, be sure to subscribe. The universe has only begun to reveal its deepest, darkest, and most delightful secrets.